Hello everyone, welcome back to another episode of Advent of Code. We're going to do day 2 today. As you can see, it hasn't quite been published yet, and I'm not starting, I'm not actually going to do the puzzle right away. There's a couple things I wanted to talk about in regards to yesterday's puzzle and some updates some slight changes I made to my template for future problems. As you know, I don't really try to compete on time, so the fact that I won't be starting right on time is no big surprise. So what have I done? I guess mostly, well, let's just see what I did, right? Oh, well, some of these won't be very interesting. So I put a little comment in here, because hey, if someone ever finds this repo, maybe they'll be like, hey, why do you have 2 versions of this? And so I put a comment in explaining why I did this silly thing. But the kind of bigger change I made is to my template here, which is to have this type. Well, first of all, here, right? I'm actually reading the file as a file from inside of Haskell instead of using the shell to redirect. I think that's a slightly worse API, if you would, a worse interface to my program. But it is very nice in Haskell, in Emacs, to just be able to run main in the REPL and it runs the thing, so I don't have to keep switching back to the terminal, right? I've also extracted out this type called input, which is basically represents part 1 and part 2 do independent things, but you're gonna want to do something in common for each of them, some kind of parsing or whatever. So I've called that the prepare step. That produces an input, and part 1 and part 2 both accept an input. If I want the input to be of some different type rather than list of string, I can just put the input. I can change the input type once, and both part 1 and part 2 and prepare will all have their types updated automatically. In fact, in day 1, in fact my type for input is a list of int, not a list of string, and my prepare function is map read and lines, right? Pretty simple. And there's a bunch of stuff where I updated every other project to use this template, so we won't show you that. But yeah, that was the main thing. The other thing is something that I didn't actually commit because I don't plan to commit it. But you remember I was trying to write this before, right? Join cons fuel. Not because I thought it was necessarily a better way to write things, but just because whenever I see duplication like this, I say, there's this name duplicated here, or some code duplicated, some code, which may be a name or some more complicated expression, duplicated. And I try to think about how do you get rid of that duplication? And maybe it doesn't end up yielding better code, but it's at least something to think about. And so I know that in the function monad, join takes a function of 2 args and returns a function of 1 arg that applies the original function twice. But I couldn't get it to compile, and the reason is I always forget. Everything in monad is in base, in prelude, except join, which is not. I wish it were, and I always forget. So if I'd read the error message I was getting more carefully, I would have realized it was saying that join is not in scope rather than that join has the wrong type. If you wanted to, you could indeed write join cons fuel here. And that doesn't seem like such a big improvement. But then I realized, well, okay, now we're only using fuel once, right? So we can inline it. What? Really? I thought I cut this, and I was trying to paste it here, and it didn't work. But we can get rid of that little where clause. Isn't that nice? So I don't know. Is this really better? I think that no. Using recursion schemes makes this confusing enough, and using the monad instance for functions to avoid duplicating to avoid naming a local is not a very nice thing to do to anyone who will be reading this code in the future. But I just this is the kind of thing that can show dividends in other programs, perhaps, and so I try to keep an eye out for it. Is when there's duplication, try to understand where that's coming from and what abstraction already exists to handle that duplication for me. Okay, so let's move on, having talked about all that, to day 2. Day 2, 1202 program alarm, or perhaps 1202 or 1202. On the way to your gravity assist. All this like astronomy stuff, right? It's like, or astrophysics, right? It's like, go back and watch my KSP, my Kerbal Space Program playlist. I was not very good at that game, but okay. Anyway, on the way to your gravity assist around the moon. Do we usually capitalize the M in moon? The moon? I think it's correct, but I don't usually see people doing it. Interesting. Anyway, your ship computer beeps angrily about a 1202 program alarm. On the radio, an elf is already explaining how to handle the situation. Don't worry, that's perfectly normal, but the ship computer bursts into flames. What is this a link to? Halt and catch fire? Yes, halt and catch fire. You guys, you can't see the tooltip. Also, you can't see my mouse? I'm not sure if that's a good thing or a bad thing, by the way. I noticed that when I was watching yesterday's video over. It's good because when I'm using the terminal, I often forget to move the mouse out of the way. Can I change it so that the browser does capture my mouse? Okay, wait, what just... Oh, okay, I'll be right with you. When I changed the capture settings for the browser, it lost the window it was watching. But okay, so now you can see this, and if we go back here, you still can't see it. Okay, so that's perfect. So let's have it that way. Anyway, halt and catch fire is what this is a link to. You can't see that either. Apparently it doesn't capture tooltips. That's fine, I guess. Or not tooltips, but like the Chrome pop-up thing in the bottom left that tells you what it's a link to. Anyway, you notify the elves that the computer's magic smoke seems to have escaped. The computer ran int code. Was this like the thing we did last year? I don't know. Int code programs like the gravity assist program it was working on. Surely there are enough spare parts up there to build a new int code computer. This is a weird paragraph. I don't totally understand. Like, they're introducing all this int code stuff. Whatever. An int code program is a list of integers separated by commas, like so. To run one, start by looking at the first integer, called position 0. You'll find an opcode, either 1, 2, or 99. 99 means the program is finished, and if it's not 1, 2, or 99, something went wrong. Opcode 1 adds together numbers read from 2 positions and stores the result in a third position. The 3 integers immediately after the opcode tell you these 3 positions. Okay, yes, very good. Position read, read, write. Okay, and we're adding, yes? Opcode 2 multiplies instead. And both of those take exactly 4 positions, right? The opcode, 2 reads and a write, so we step forward by 4 to do something. And I assume that this will be sort of interesting because we end up rewriting the opcodes that we're going to later execute. One, yes, okay. They represent the first opcode. Addition, the position 9, which should be this one. Yeah. So we read the 30 and the 40, and we write them here. Oh, no, position 3. 0, 1, 2, 3. Oh, it's overwriting the 3 itself for whatever reason. Okay, step forward 4 steps, and okay, great. So just do this, and then you get to 99. So before running the program, replace position 1 with the value 12 and replace position 2 with the value 2. So our program input is like a bunch of ints. Not even all that many, interestingly. You could do this one by hand if you had to. I wouldn't recommend it. And then we run the program and see what's left at position 0. All right. So this shows up something that I'm like not as experienced in Haskell as I would like to be, which is like how to use friggin' arrays. Anything where you need integer offset, right? Linked lists and lazy linked lists in particular are great for like accessing things sequentially, but here we kind of need random access. And I know that Haskell has array support, and in one of the problems last year, I did figure out how to use arrays barely. It's just like a gigantic pain. So I think what we should use instead is intmap, and let me just look real quick. Haskell intmap. What package is that in? It's in containers. Okay, so I have it already. Data intmap, right? Okay, so I can just use an int map. Honestly, an ordinary map would also be fine, but it's sort of nice to be optimized. This function is being removed. Wild, okay. They have data int map strict and lazy now instead of prime suffixed versions. Okay. So the other thing that I'm not sure about yet is with my Emacs setup, how do I, like right now my REPL is attached to this file, and when I open another file, I believe its default behavior will be to reuse the same REPL, which is like, oh no, it opened a new one. Very good. Okay, cool. Okay, so we'll import this. Yeah, and it's warning me I'm not using it, but that's fine. That was sort of the point. And our input is going to be a list of int again. What is a good way to split on commas? They're all positive numbers, right? Yeah, so I think I'll just cheat here and say, it is, yeah, get out of here. I still need to be able to see my source file. Don't just give me a giant error. So we're just going to say read of, we're just going to like do this, and it's pretty gross, but it works. And in fact, actually our input should not be a list of int, but it should be an m.map to int, right? Is it an int map, I guess? Okay. So this read, of course, is not correct. We need to... how do you build an int map? Where's the... I don't want synopsis. Oh, I'm in... Okay, this module re-imports the lazy function. Okay, so let's go here, map construction, and the type is just a value. Empty singleton from set. Not quite. From list. Yeah, okay, so we just want like from list of zip with a range of ints, basically. Oops, I typed flip for no reason. I meant to go type from list. From list wants list of pairs. And so I want to apply that to zip 0 with, okay, so something like this. No. m.fromList. There we go. So that parses, which is nice. Or it type checks, yeah. So this will give us a map from int to value. And let's check that, I guess. Prepare like 1, 4, 7, or 6 for me, whatever. No parse. Okay, very funny. Can I ask what the type of this is? No. This is what I get for being too clever, huh? Okay, so what if I type like show a 1, 2? I get that, so that's about right. Oh, you know what? I bet there's a new line in there. Also, I haven't read input.txt at all yet. There we go. Yeah, there's a new line at the end. So that won't quite work. So I need to include prepare. There you go. That style, huh? Well, now I need to put it, there we go. So there'll be a new line in the actual program. And if I run main, will it actually like, yeah, it returns, no, because it's just ignoring the result of prepare. How do you, well, whatever, length should work on it. No, our list's not, oh, InMap isn't foldable. That sort of makes, no, there we go. Yeah, so, okay. 113 entries, fine. It parsed correctly, turned into an int map. I'm happy. Let's just put this back for now, though. So that's our prepare function. And we can get to writing our algorithm. Although we should really start with some types, right? Data op equals bin op of, let's call it a binary of bin op and I guess just 3 ints, right? Int. Data bin op equals add or multiply or end. Okay. So now we want a function that, like, given a position in our int map, tells me, actually, you know what we should do? We should clarify that these are positions and not just ordinary integers. Okay, so we want a function that, like, not read exactly. It's not exactly parse. It's like decode, I guess is the word, right? Input and an int, no, a position to return an instruction. right? You just math, there's no accompanying binding, right? Yeah, okay. Decode of m pos equals case m dot okay, whew. I just looked at my recording software and said I've been live for 0 minutes, and I thought I'd made some mistake, but I've been recording for 20 minutes, and it makes a distinction there. Anyway, so how do we read from int maps? Query. So lookup gives you a maybe. That's fine, I guess. And honestly, that's probably what we should use. We could use this, and that would be like, probably it would always work, but it would be sort of like more honest. You know what we could do? We could find with default and say if it's not there, give me back a terminate the program instruction. Is there a reason to do that? I think it's probably better to do stuff in maybe, because I'll want to read like 4 different things, and any one of them could fail, and it's sort of nice to just get that handling for free. So we want lookup, I think. Yeah. Is there a way to get like given a position, tell me like the next 3 items or something? I guess there is, but it's not really going to be... Ooh, submap. No, that's actually not. So, okay, whatever. We just won't do that. Ooh, show tree. Interesting. But we don't want it. All right. So we have lookup. m.lookup m pos. Actually, you know what? Let's do code to be m.lookup of m and pos. That type checks, right? Wrong order? The order of operations that Haskell's map functions take always surprises me. Okay, so apparently it takes a key and then a map. I don't quite know what reason there is for that, but it doesn't matter, obviously. Case code of, if it's 99, we return end. There you go. And it's telling me this is inexhaustive, quite reasonably. I guess we should write these above, right? If it's 1, we bin op of add, and 2 is bin op of multiply, otherwise nothing. Okay, so we haven't written bin op yet, of course. Bin op equals something. And this is actually not going to work because it's, I want it back here. There you go. Right, we don't want it attached to the last case only. We want it attached to the function. And you know what? This do is like kind of lame, but I guess it's fine. I don't want to turn on lambda case, so this is as good a way as any to do the nothing handling. So this is a longer day 2 than I expected. I'm sure there would be a simpler way of doing it, but I kind of, you know, this seems relatively straightforward anyway. It's just going to take a little while. So now we want to you know what? Let's define a little function here. At n equals m dot lookup. M dot, what is it? Bang is the one that like looks up with a maybe. Is that right? Sorry, I'm just scrolling through the docs here. Query. No, that's the one that doesn't. Okay, we want this. Did I still get it wrong? Oh my gosh, forgive my terrible typing. Oh, that's why I'm so confused. Look at this. The lookup function takes its arguments in a different order than the infix function. Why? There must be some reason that this is more convenient, but it sure makes it hard for me to remember the order of things. Okay, so we have this at function. Yeah, I guess this is fine. So now we say do a is at pos plus 1, b is at pos plus 2, c is at... Is this what I want? Yeah, I have a position. I want to look up the positions after it. And the values there will themselves be positions, but I don't want to read those. Pos plus 3. And then we... This is so dumb. I should just use lift A3 for this, right? Lift A3 of binary op this, right? Yeah. Can I import that, please? In applicative LMNOP QRS. Okay. Import control.applicative lift A3. And we don't need that do, of course. All right. So this is basically like lift A3 is handling all the stuff I was going to do with do myself, right? It says like take 3 arguments, each of which might return a maybe. And if any of them does return a maybe, just return maybe. Otherwise, call the function binary op, passing it those 3 remaining arguments. So we have up here, you know, so let's driving show, just to like show you guys what I mean. So like let's say, in fact, we can use the examples from the input here. If we look, I'll just say decode prepare this and at position 0, no parse. Right, we assumed there would be a backslash n or a new line in there. And so indeed, it parses to a binary addition operation at positions 9 and 10, writing to position 3. Exactly what I hoped it would do. Great. And multiply, of course, will work just as well, and I assume end would work. It's very simple. So now we have this decode function, and we can write like an eval function. It might kind of be nice to be in like a maybe t of a state t so that we can... Oh, that's the other thing that I put in my imports last year that I haven't done this year, is like some monad transformer library, whether it's MTL or the other one. I forget. Monad trans, I guess, is maybe what it's called. Anyway, we don't really need it here. We can handle the maybe and manage the state by hand. It's pretty simple. So we can write a function called eval, which takes an input. And you know what? Calling this an input is kind of dumb, right? Input is a useful alias, and I want to keep it, but we should also have type computer program. Any inspiration here? Int code program? I don't know. We'll just call it program. It's the same thing. It's like a set of registers, basically, right? And in fact, let's just say there. So now this function doesn't really take an input so much as it takes a program. And we want another program function, eval, takes a program and a... Is this the right order to... I feel like it might be better to swap the order of these two arguments. Doesn't, like... I don't know. We'll see. Okay, so maybe program is kind of not correct, isn't it? Because the program might terminate for two reasons. And we always want a program back. Right? Well, no. Because when the program ends, its state won't have changed, and so we can just like look at what the program was before we ran eval. Okay, so we'll say maybe program should be okay. So there you go. We have an incomplete pattern match, but that's partway done, right? And otherwise, we have eval m of bin op, no, binary of op from 1, from 2, source 1, source 2, like proper assembly programmers, right? And dest. And you know what? I don't know. I feel kind of silly about taking this at thing, reusing it again. But I think it's sort of still useful. Right? Yeah, all these things are unused, but it type checks, and that's all I was looking for. So what happens is does the problem specify what should happen if we write to a position that doesn't exist? It doesn't say. I'll just ignore that possibility and write to there regardless. If it makes the program expand, who cares? It shouldn't happen, so I'm just not too worried about it. Okay, so do we kind of want to do here, sort of? Yeah, why not? And what we're going to do is say, result to be lift a2 of run bin op on source at source 1 and at source 2. And we need to implement run bin, of course. let's put it up here near bin op. Run bin of add equals plus run bin of multiply, oops, I don't need parents there, equals times, and like that's all. I guess I should give it a type, huh? Run bin takes a bin op and produces a function from int to int to int. I say produces a function, right? This would be equivalent. And arguably, this is probably a better type. I think these parents are nice. So we're sort of using it higher order anyway, right? So, all right. So now, like, this all type checks. We're just not using the result yet. And what I should do is say pure of m dot, how do you write to a map? There's alter, insert, I guess, is the function I'm looking for, right? Insert takes a key, which here is our position, destination, and then it takes the value, which is result, and then it takes the map. There you go. And so if at any point any of these reads, produce a nothing, then our eval program will stop. It would sort of be nice, wouldn't it, if like eval could somehow tell you how many instructions it consumed, right? What I'm worried is that I'm gonna find like part 2 is saying, oh, by the way, there's this other operation that takes 1 input, and like everything I've written so far is, well, I guess what we could do in that case is augment instruction to tell you how many opcodes it consumed. And then that should be okay. So I don't think I'm building anything too brittle by currently assuming only binary operations exist. And really it's kind of a ternary operation because it consumes a write slot as well. But okay, so now I think we're about ready to write part 1. We take a map, and we need to do a few operations on it. We write a couple times to it. What is it we're writing? We replace position 1 with the value 12, position 2 with the value 2. So how do you insert like multiple times? There's like a merge or something. Combine, I guess I want a union. Left biased union. It prefers the first map. Okay. So let program equal m.union. Ugh, this is silly. I'm gonna have to build a map using from list, and like, why don't I just call insert twice, right? M.insert. What's the type signature of insert? Key and A. Okay, so that's actually a useful order. Insert at position 1 the value 12, and then insert at position 2 the value 2. Okay, so now we have our actual program. And last, what I want is to like iterate eval, but I don't quite want eval, right? I need something that like I need like a tick function that takes an instruction and a program and returns maybe, not an instruction, an offset and a program, and returns maybe a new offset and a new program, right? So let's write that. Tick takes a program and a position and returns maybe. And here's why I was thinking, like, maybe we need to lift some of the offset into being part of the type somehow. But for now, I don't know. We'll see. Tick of P. I've been calling them M, and now they're P. I don't know. Whatever. Now that and pause equals well, first we're going to decode. What's the type of decode? Takes the input. Oh, I haven't loaded this in forever, huh? Now it doesn't compile, so I can't load it. Okay. Decode has type program first, then position. Okay, so we have this. We've gotten a maybe of an instruction. Well, whatever. We'll just write with do notation. And then we want to eval P prime will be eval the program and the instruction, and then it will return pure of pos plus 4 and P prime in a tuple. There you go. So this is where it's a bit like hard-coded, more than you might like. What is this? Redundant bracket. That's true. I guess I didn't need that. That is better. Thank you, HLint. So now we can basically, like, not exactly iterate tick because we have to unwrap the maybe every time. Does iterate M exist? It's not what I want anyway. Never mind. Unfold, fold M. None of those seem to quite fit. Actually, what is iterate M? Iterate M. Well, this is in streaming, which I don't really want to pull in. Yeah, people have these in various packages, but it's not actually like part of base, and I don't really want to mess with any new libraries today. This is, I don't know, none of them are really what I wanted anyway, so. So I guess what I sort of want is just go of this, where go of program equals something, like, I don't know. Case tick. Oh, go. I guess we need to start with a position, huh? Start with 0. Nothing. Then we return what the program had before, which should be position 0. M dot lookup. And what order does lookup take? I'm never going to remember. Query lookup key first. Okay. Offset first. Why is this not type check? Oh, because I said it returns unit. It should instead return maybe int, I guess. Oh, yeah, you're right. Good suggestion, HLint. We don't need this m at all. We can just compose together 3 functions. All right, well, that's interesting. It all type checks. We wrote some kind of reasonable looking stuff. Let's see what happens. Main. A number. Okay. I mean, that's pretty good. All things considered, a lot worse things have happened to me in my life than getting a number when I ran a program and I wanted a number. We'll see if it was right. That's the right answer. Cool. So, all right. I guess let's commit this. Day 2, part 1. All right, and move on to part 2. Good, the new computer seems to be working correctly. Keep it nearby during this mission. You'll probably use it again. Okay, they're hinting at us to like put this in a library or something. Real encode computers support many more features than your new one, but we'll let you know what they are as you need them. Okay, so didn't we have like last year or maybe 2 years ago a number of programs that were building on like an interpreter of some sort? All right, anyway. However, your current priority should be to complete your gravity assist around the moon. For this mission to succeed, we should settle on some terminology for the parts you've already built. Okay, I wish I'd known the terminology before I named everything in my program. Encode programs are given as a list of integers. These values are used as the initial state for the computer's memory. When you run an encode program, make sure to start by initializing memory to the program's values. A position in memory is called an address. For example, the first value in memory is at address 0. Opcodes like 1, 2, or 99 mark the this is a lot of words. Mark the beginning of an instruction. Okay, so this is like kind of telling you what names I should use for everything. The values used immediately after an opcode are called the parameters. Yeah, fine. The address of the current instruction is called the instruction pointer, which starts at 0. After an instruction finishes, it increases by the number of values in the instruction. Where did we define a value? They haven't told me what the word value means, which is interesting. But okay, I guess they just mean like the number the instruction consumes. So that was kind of the stuff I was talking about. Maybe we should like an instruction should somehow be enriched with like information about how many bytes or how many integers it consumed, right? And an instruction should be enriched like that, but a program should be enriched with an instruction pointer, right? If we were going to model a computer more faithfully, we would do stuff like that. And it sounds like we're going to be using this computer many times, so we should consider doing that in a future version of this program. Blah, blah, blah. So until you... Yeah, this is always 4. The halt program would increase by 1, but it doesn't matter. Yeah, so that's sort of what I did. To complete the gravity assist, you need to determine what pair of inputs produces the output and then some large number. The address 1 is the noun, address 2 is the verb. They'll each be between 0 and 99 inclusive. Interesting. I wonder if there are going to be inputs, if like for all inputs the information is, the program is well defined, or if some of these inputs will cause us to overwrite. Yeah, surely some of these inputs, well, I was going to say surely there's some set of inputs that makes the program illegal by overwriting an opcode to be something other than 1 or 2, but that might not be the case because we don't have access. We can't change the position that we write to with the first operation. We just change what value we write there. And as long as the program, as long as Eric was careful to produce the program input in such a way that it never like could possibly interpret that as an address to write to or read from, then it'll sort of be fine. Now maybe he didn't do that. Maybe he wants you on purpose to like have to deal with crashing programs or something. But I don't think that is. He would have told us what should happen if you write. Well, actually, he does tell us, right? He tells us if you read something else, something went wrong, and maybe, but what should you do? Something anyway, it doesn't matter. So, all right. So we just need to. Probably abstract out something from part 1 that takes like a noun and a verb and produces some value. And produces, I guess, the output, right? So let's write a function called run, which takes a program and a noun and a verb. You know what? I'll just call those ints, I guess. And produces then maybe an int, which is like what was at. Let's just produce a program. And you can look at position 0 if you want, but you can do other things if you want. Run p noun verb equals, and now we'll basically take all this stuff. I bet noun verb p would be a better order to do things in, actually. Noun verb. Yeah, see, because okay. Part 1 is how did I get an int out before? Oh, here. Okay, so part 1 is there should be a type mismatch here, right? I'm not handling the maybes or something. What is this couldn't match type thing? What types does it want to match? Oh, I claimed it takes a position and returns a program, but it takes a program. Okay, so it actually does type check. Great. And so this could, in fact, just return an actual int, I think. Run 12.2. And then, this is what I need the maybe for, is there might be... No, there will always be something at position 2. But the map doesn't know that, I guess, so... there you go. So if we do this again, and we run main again, we get... Was that the same value? Yeah. Okay, so this little refactoring has kept the program intact. And we can implement part 2 using that new refactoring. So I guess in principle this should return a maybe int, right? Because maybe none of them would do it, right? So part 1 of or part 2 of P equals, you know, let's actually, we'll return a list of ints, or a list of pairs of ints, I guess. The noun and verb pairs that work, and that way we can just throw all this into a do on lists and it'll all be very lovely. Oh, and I guess our input in principle is like, okay, so we wanted, oh, actually it wants just a single int for reasons that are kind of silly, right? Because he can't accept a tuple as a result, right? So he wants you to take 100 times the noun and add the verb, and that way you get a single number out of it, whatever. I'll have my program produce that. Case run, no. This is so dumb. It should just be like a lift A2 over there's 0 to 99 twice. But we'll give them names for case run P noun verb of nothing. Well, that would be quite a shock, wouldn't it? But we'll just return nothing, or return an empty list, and otherwise, and if the result happens to be just this, or yeah, that's the output we want. 100 times noun plus verb, and otherwise, oh, nothing. Oh, run wants its arguments in the other order. Okay, well, that's kind of cool. It type checks. We'll see what happens, right? 6577. We got, as we might have hoped, a single output. So let's see what happens. That's the right answer. Cool. So here's our advent calendar. It's sort of not clear what's happening yet. Maybe this is a planet with a ring? Huh? Could be. Kind of looks like a field of stars up here. We'll see. So anything to say about this program here? Like, we should git commit this, and I will soon. But I just want to see, like, is there anything that I'm sort of missing here that would have been, you know, cooler? One thing is, like, there's exactly one place in this program where I used some recursion, right? Everything else just sort of... well, where I wrote recursion manually, right? This go here is the one place in my whole program where I had to write a loop myself. And since I was trying to play with recursion schemes, it would be sort of nice to, if I could, figure out like what operation this is. Like, is this another anamorphism? Sort of like, I mean, it's like an iterate, but like getting the nothings out is kind of weird. Yeah, I don't know. I don't think I'm gonna mess with that today. We'll just commit this and move on. If I type very fast, we can be done in under an hour. Ah, too slow. All right. So we did sort of do two things today, and I could think of splitting it up into two commits. But I don't think I will. I think I'll just like add it all as one big old chunk. And this is kind of the scale of the refactoring that was necessary to implement part 2 as well. And it's not bad, right? I just like, you know, basically renamed part 1 to run, and a small piece of what used to be part 1 was extracted back out into the new part 1. And then I implemented part 2 using that same tool. So, not bad. A little tacky, like, is this number the same for everybody? Not sure. You know, is that really part of my input and not part of my program? You could argue about it. But it was very nice to have the program, each time that I like thought I was done, like it just ran and it gave me the right answer the first time, which was sort of nice, right? It's a sort of complicated simulation program to write. Like not super complicated, but there's a lot there. There's places you could make mistakes, and the type system helped me get it right. I don't know. I think there are a lot of ways I could have made mistakes here that the type system would not have caught. And it's definitely not like a monument to simplicity or anything like that. But we can clean it up for the future days that are going to reuse this whole int code thing, and have proper modeling of the computer. Like things I'm not happy about are like this, right? A computer should sort of know its position, but I didn't know when I was starting this like where exactly it was all going, and so it's a bit messy. There shouldn't be two arguments. There should just be one argument that has two things. You know, here maybe it's fine, but it should like return a new offset or something like that. So there's some cleanup to do, but the program is fine. And I guess that's all for today. We solved the puzzle. Hooray! Thanks for watching, and I'll see you next time.